So as a first example of applying Lagrangian calculus together with Gateau derivatives, we would like to consider our ODE example. And it looks like this. So it's u dot of t and z minus f of t, u of t and z equals to 0, and u of 0 z minus z equals to 0. Yeah, so that's again the implicit relationship equation equals to 0. And what we do here, what the parameter is, the parameter is the initial condition. So if on one parameter z, but we have a general nonlinear ordinary differential equation. So here, the initial condition is uncertain. Yeah, and to make things a little bit more interesting, I've made the right-hand side general. So the key to applying the Lagrangian calculus and Gateau derivatives to differential equations is to explain what Lagrange multiplier times equation actually is. And it is the inner, well, I've written it as a transpose, so it's a scalar product, so it's an inner product, and so it needs to be the inner product on the function space. So that's the answer. So we have to take the inner product on the corresponding function space, and function space, and that's now the integral of the product. Yeah, so lambda transpose times E of u and z is actually the integral from 0 to t, lambda of t. So the Lagrange multiplier now is a function itself, and the constraint is this one here, almost this one. So we do something as before, integration by parts, in order to include the initial condition into this. So there's many ways of doing this. I'm opting for this. I could also introduce another Lagrange multiplier and add this condition in here as well. But I can also do it like this, start with just the differential equation, then use integration by parts. So we have minus u of t lambda dot of t. So I'm moving the derivative onto the other term. I don't have to do anything for the right-hand side, lambda of t. And if I do this integration by parts, I obtain a boundary term, u of t lambda of t, in the limits 0 to t. And at u0, I know that one of these terms is actually equal to z. And that's the way, or this path of including the constraint into the problem. And I would recommend to you to try the other way yourself. So add an additional multiplier for the initial condition and compare what you're actually getting. And ultimately, you should be getting the same result, because it's just a different way of modeling this. So here I would get minus u of 0 times lambda of 0, and I've substituted the u of 0 with the z, and that's how I included, I'm repeating myself, the initial condition. Okay, well, now I have established what the scalar product term in the Lagrangian is. Now we can start computing. So assume the following QOI. It's supposed to be R of U. Simple, so we take the square of the solution U at the final time. Just because it's something that we can compute. And now we can put together the Lagrangian for this problem. So if we take L of u, z, and lambda, u and lambda now being functions, z being a scalar, I have my functional and I'm subtracting my formulation with the integration by parts. So that's 0t. And then I have minus u of t, lambda dot of t, minus f of t, u of t, lambda of t, dt, and the boundary terms, minus u of t, lambda of t, plus z, lambda of 0. And now in the Lagrange calculus, I need to compute the derivatives. Well, so let's start with the simplest one, the z derivative. So if I look in this equation, where is there an explicit z dependence? That's kind of simple. It's only here. And so my z derivative is just lambda evaluated at 0. So it gets a little bit more interesting now with the other derivatives. So let's look at the u derivative. And again, now I have to formulate this as a Gateau derivative. So it's the derivative with respect to u in the direction v. So I'm writing down the result now because we've done the computation essentially in the last video. So let's look. I have the u here, and if I differentiate this, I get the square that cancels with the 1/2, and then I get a u of t times a v of t because I'm taking a directional derivative. Then where else do I have the u? I have the u here, but it's a linear term, so the u is just substituted by the direction v. Then I have the u here, that becomes a u derivative of f times v. And then I have the u also here, that just becomes a v times the lambda. Yeah, so I'm jumping over this or going over this quickly. I'm not doing all of this by hand, but I would recommend to you, if you don't have enough exercise yet, to compute this by hand yourself. Yeah, so the first one was a u of t times a v of t. That was the u of t square term. And that should be a capital T, of course, like this. Then I have my integral minus 0 to t. Then I have a minus v of t, which substitutes the u of t, the lambda dot, then minus a d over du, f of t, u of t, times v of t. And actually, I should take this into the next line here. U of t, v of t, times lambda of t dt. Yeah, so this was derivative with respect to u, direction, and I just copied the lambda. And then the final term is minus v of t, lambda of t, which was just a linear term in all of it. And so we can put the first and the last term together. So we get this. It's a u of t minus v of t, lambda of t, minus the integration. So minus integral 0 to t. Then we have minus v of t, lambda dot of t, minus d over du f of t, u of t, v of t, lambda of t, dt. And I actually missed the brackets. Yeah, so that's the way it looks like. Now the direction v is arbitrary. So that means that The second term, if I say, well, my v is in a sense arbitrary. Oh well, I've missed something. So let me also take in the second term. Let me take out the v. Yeah. So in the integral, there's a v here and there's a v here. So let me rewrite this one, and then I can argue actually. So let me take out the v. So this is actually a v of t, and then I have minus lambda dot of t minus d over du f of t u of t times lambda of t, brackets closed. Okay, so so v is arbitrary, right, as a direction. So that means if, and here I've also made a mistake in the first term. So now my argument becomes clean, hopefully. So it's actually a u of t minus a lambda of t times v of t. Okay, now it makes more sense. So now if I took out the v out of both terms, so the v is in a certain sense arbitrary, so I can say whatever value I assume for v of capital T. Yeah, so I have many functions there, and I have many choices of the function here. And that actually means if I vary both of them, for the whole thing to be zero, which we want, right? So that's the demand of the Lagrange calculus. For this to be zero, we can vary v, and we can see that actually both terms individually need to be zero. Yeah. So that means since v, the direction is arbitrary, the conditions from the total derivative must be satisfied, so both terms need to be zero individually. And that means I can read off an ordinary differential equation, yeah? So thus the multiplier lambda satisfies the following ordinary differential equation, and I'm writing down the term already, so the backward ODE. And why is it called a backward ODE? Because it looks like this. Minus d over du f of t u of t, lambda of t equals to 0, and lambda of capital T equals 0. Yeah, so because of the integration by parts, I get a minus sign on the time derivative, which kind of tells me it's backward in time. And that makes sense because I'm fixing the final condition. Yeah, so it's an ordinary differential equation that I need to solve on the interval capital T to 0, and I'm starting at the final point in time. And then putting this all together, I would solve this backward ordinary differential equation, which you remember coming from the adjoint calculus is also called the adjoint ordinary differential equation. I solve it, I compute the solution at 0, and the solution at 0 is the value of the derivative of the reduced cost functional. Yeah, so what I need to do in this ODE example is solve the forward ordinary differential equation. That gives me the solution u. That needs to go in here. I solve this linear backward ordinary differential equation, compute lambda of 0, and that's actually the sensitivity. So we therefore solve the forward ODE for u of t, solve the adjoint ODE for lambda of t, and obtain the sensitivity by evaluating lambda of 0. Yeah, and that's typically what you see from the adjoint calculus when applied to an ordinary differential equation. So forward solve, backward solve, evaluate, and that's the quantity of interest here.